Have you ever actually wondered what's inside a 5G base station? I mean, it's not just some magic box on a pole. Today, we're going to pry it open and take a look at a really revolutionary new way of thinking called ORAN. That's Open Radio Access Network. It's completely changing the game for how mobile networks get built. Okay, let's get into it. For the longest time, building a radio network, the RAN, was kind of like buying a Mac. You got everything from one company, the hardware, the software, the whole shebang. And yeah, it worked, but it was a total black box, closed off, proprietary. Well, ORAN throws that whole idea out the window. It's much more like building your own custom gaming PC. You get to pick and choose the absolute best parts from different companies. Maybe you want a radio from one vendor and the processing software from another. And it all works together because everyone has agreed to speak the same open language. All right, so here's our game plan. We're going to start with why the old closed way was a problem. Then we'll get into the really clever part, how ORAN splits up the network. From there, we'll dive into how all these new pieces talk to each other, see how open source software makes it real, check out the specialized hardware that gives it a power boost, and then we'll wrap it all up with why this matters to, well, all of us. So what was the big deal with the old way? It really comes down to one phrase: vendor lock-in. If your network was built by Company X, you were stuck with them for everything. Upgrades, new parts, all of it. And as you can imagine, that really slows down innovation and, let's be honest, it keeps prices high. The whole point of ORAN is to smash open that block box and turn it into a set of Legos, standardized building blocks anyone can use. Okay, so how do you actually do that? How do you turn a single black box into a bunch of building blocks? The core idea, the absolute heart of ORAN, is to split up the jobs a base station has to do. Instead of one giant monolithic thing, the work gets divided into these very distinct, standardized chunks that different companies can focus on and perfect. What's really fascinating is how this split actually happens. There were a bunch of ways they could have done it, but the ORAN community landed on a specific method called the 7-2X split. Now, this carves up the base station's work into three main components. You've got the CU, the centralized unit for the high-level planning, the DU, or distributed unit for the heavy real-time work, and the RU, the radio unit, which handles the actual radio signals. And as you can see in the diagram, this split happens right smack in the middle of what's called the physical layer. That's the part that literally turns ones and zeros into radio waves. Let's zoom in a bit on the ODU. You can think of the Open Distributed Unit as the really busy, real-time manager of the radio. It's running all these critical functions, making split-second decisions about who gets to send data, when they get to send it, and how the radio's resources get shared. It's a real workhorse. And then we have its partner, the ORU, the Open Radio Unit. If the DU is the manager, the RU is the part that's actually on the front lines, doing the talking. It's the antennas and all the gear that takes the digital commands from the ODU and transforms them into the radio waves that your phone can pick up, and, of course, does the same thing in reverse. So here's the absolute linchpin of this whole thing. For an ODU from Company A to work with an ORU from Company B, they have to have a perfectly defined, totally open way to talk to each other. That connection, that critical communication link, is called the front haul. And honestly, it is the magic that makes this entire multi-vendor world possible. But here's where it gets even more interesting. The communication happening over this super fast front haul connection isn't just one simple data stream. It's more like a super highway with 4 different lanes, all happening at once, and each lane has a very specific job. In ORAN, they call these the 4 planes of communication. And this diagram just lays it all out for us perfectly. You've got the control plane, the user plane, the synchronization plane, and the management plane. And you can see how each one is optimized with a slightly different set of protocols to get its specific job done right. So let's break down what each one actually does. First up, the C plane. Think of this as the air traffic controller for the radio. The ODU is constantly sending instructions over the C plane to the ORU, telling it exactly what to do, when to do it, and even how to shape the radio beams for the best performance. This is the traffic that's running the whole show in real time. Next is the U plane, and as a user, this is the one you really care about, even if you don't know it. The U is for user, and it carries your actual stuff, the raw digital data of your Netflix stream, your file downloads, your video calls. This is the main highway for all your personal data, and you better believe it gets top priority on the network. Now, the S-plane is kind of like the network's conductor or a super precise metronome. Its only job is to carry timing information that keeps every single radio unit in the network synchronized down to the nanosecond. This might sound nerdy, but it's absolutely essential for advanced 5G stuff, like making sure you don't drop a call when you're driving from one cell tower to the next. And finally, we have the M-plane. This is the backstage crew, the IT department for the whole operation. It's used for all the management and admin stuff that doesn't have to happen in a split second. Things like setting up a new radio for the first time, configuring it, checking for any problems, or pushing a software update. It's the behind-the-scenes workhorse. Okay, so having a great open standard on paper is one thing, but you need actual code to bring it to life, right? And this is where the amazing open source community comes into the picture, proving that this complex new architecture isn't just a theory. They're actually building it. And a fantastic example of this in action is the SRS RAN project. As their team puts it, it's a complete 5G RAN solution, and crucially, it was built from day one to be O-RAN native. This is a real, working software version of the CU and DU that anyone can actually download and experiment with. It's incredible. I mean, the existence of projects like SRS RAN is just huge. It's proof positive that the O-RAN model isn't just an idea, it's a reality. They've built the software for the CU and the DU. It supports that super important split 7.2 front haul interface we've been talking about, and you can even run it on different kinds of computer chips. It makes O-RAN real. So software gives us all this amazing flexibility, but there's a catch. The amount of data flying across that front haul, especially on the U-plane and C-plane, is just astronomical. Trying to process all of that at 5G speeds using just software on a normal computer chip is a massive, massive challenge. Sometimes you just need a hardware boost. And this is where the puzzle pieces really click into place. What you're looking at is a diagram of a specialized hardware block designed by Intel. It's an O-RAN processing core that runs on their FPGAs, which are basically super flexible, reconfigurable chips. And look, right there in the diagram, you can see a C-plane mapper and a U-plane mapper. This isn't software. This is a chunk of silicon purpose-built to do one thing: handle those C-plane and U-plane messages we just learned about at absolutely blistering speeds. And just to give you an idea of the kind of horsepower we're talking about, just look at these numbers. This table shows how many of the resources on a really powerful FPGA are needed just to run this O-RAN core. With data compression enabled, we're talking nearly 50,000 logic modules and over 81,000 logic registers. This is a serious piece of hardware, which just goes to show you how complex and demanding that frontal really is. Okay, so we've gone deep. We've gone from the big concept of opening up the network, down to the 4 lanes of communication, and all the way to the real software and hardware that makes it happen. But let's roll back up. What's the big payoff? Why does all this technical stuff actually matter? Well, it really boils down to this. For the companies that run our mobile networks, O-RAN shatters that vendor lock-in, finally giving them real choice. It opens the door for smaller, more innovative companies to create amazing software without having to build everything from scratch. This means networks can be customized for specific jobs, and of course, when you have more companies competing, it drives innovation up and helps bring costs down for everyone. So what we're really seeing is this fundamental shift. Our huge global mobile networks are starting to act more like the open world of the internet, or even our own personal computers. They're becoming platforms. And that leaves us with a really exciting question to think about. As these networks become just as open and customizable as our PCs, what incredible new applications and innovations will a whole new generation of creators and developers build on top of them?